Okay, so today we're going to talk about something called the limiting reagent, or sometimes you'll see it as the limiting reactant. Okay, so if you hear limiting reagent, limiting reactant, we're talking about the same thing. Okay, so the limiting reagent is just whatever reactant runs out first in that chemical reaction. Okay, so just like that activity we just did with the nuts and bolts, right? Whichever one runs out first is what we call the limiting reactant or the limiting reagent. The reason why we call it limiting is because it limits the amount of product that you can make. Okay, so once you run out of that reactant, the reaction stops, right? You can make no more product after that. Okay, go ahead and copy down this equation. So we have the sodium plus the chlorine gives us sodium chloride. And we're going to figure out if we have 6.7 moles of sodium reacting with 3.20 moles of chlorine, which one of those is limiting, or which one of those is going to run out first? We're going to do some math. So we're going to start this one just like we've started all of our others. So we're just going to identify what's known. So how many moles of sodium are we starting with? Okay, so just under that equation, I'm going to write 6.7 moles of sodium. Okay. And then how many moles of chlorine are we starting with? Okay. So this time we have two starting numbers. So how many equations? Two. So we'll do two different calculations. We only have one product, so we'll figure out how much sodium chloride they can each make. In this one, it doesn't tell you what kind of unit of sodium chloride we need, so we'll just keep it in moles because that'll keep like our calculations simpler. All right, so we'll do two different calculations. I'm just going to start with sodium first, solely because it's listed first. So we're starting with 6.7 moles of sodium. And then what's the ratio between sodium and sodium chloride? 2 to 2. Okay, 2 to 2. So for every 2 moles of sodium, we get 2 moles of sodium chloride. Okay. So how many moles of sodium chloride can we get? Okay, so we get 6.7 moles of sodium chloride. So that's just half the battle. Now we're going to do the same thing. This time, we're going to start with the 3.20 moles of chlorine. Okay. So now, what's the ratio of the chlorine to the sodium chloride? Okay, it's a 1 to 2 ratio. What's 3.20 times 2? 6.4. I'm going to rewrite that. That looks terrible. Okay, so 6.40. So now we have two answers. How do we know which one is like the actual amount we're going to make? 6.40. Okay. Always the smallest number. So we know that this reaction's only going to make 6.40 moles of sodium chloride. And then we just have to pay attention to what you're actually being asked to figure out. So this time we want to know what's the limiting reactant or limiting reagent. The reagent is always implying to the reactant. So is it the sodium that runs out first or the chlorine? Okay, it's the chlorine because it's the one that comes from the calculation that makes the smallest amount. So then the way we answer this one, the limiting reagent is the chlorine. Okay. So for this one, we're not looking for a number as the answer. We're looking for like a word. Okay, we're going to do one more limiting reactant problem. It's the same thing. This one's just asking for a different type of answer. Okay. So we're going to figure out how many grams of hydrogen can be produced when 6 grams of hydrochloric acid and 5 grams of magnesium are reacted. So start out by just writing down that chemical equation. And then next, we're just going to list what we know. So how much magnesium are you starting with? Five grams. And then how much hydrochloric acid are you starting with? 6 grams. All right. And then which product are we interested in? Okay, so we're interested in the hydrogen, so I'm going to put that question mark under hydrogen. In what unit are we interested in? Okay, so I'm going to put the G for grams. Okay, so for this one, you have 2 starting numbers. So how many different calculations? 2. Okay, so we'll do one where we go from grams of magnesium to grams of hydrogen, and then we'll do grams of hydrochloric acid to grams of hydrogen. Okay. All right, so I'm just going to start with the magnesium. So we start with 5 grams of magnesium. And can we just go from grams of magnesium to grams of hydrogen? Okay, what unit do you have to convert to? Okay, we've got to convert to moles. So how do we get from grams to moles? Okay, what's the molar mass of magnesium? Okay, so 24.31 grams of magnesium is how much 1 mole weighs. All right, and then now what's the ratio of magnesium to hydrogen? 1 to 1. So for every 1 mole of magnesium, we get 1 mole of hydrogen. And then finally, we want the answer in grams. So how do we get from moles to grams? What has to go in that top box?
Molar mass.
Good. Molar mass. What is the molar mass of hydrogen?
1.0.
Okay, and what's special about this one?
It's diatomic.
Diatomic. So what do you have to do to the mass? Double it. So it becomes 2.02 grams. All right, so now you're going to calculate it just like you normally would. Does anyone have a number? 4154.
And change.
Okay, that's probably good enough. Do y'all agree with that? Okay. Are we done? We'll do that at the very end.
Technically 415.
415. Okay. I hope that our 2 answers aren't going to be that close. Okay, so now we have to do a whole second calculation. So this time, we're going to start with the HCl. Okay, so we have 6 grams of the hydrochloric acid. Can you just go from grams to grams? Okay, what unit do you have to convert to? Moles. Okay. So what's the molar mass of hydrochloric acid?
36.46.
Thank you. Okay, and now what's the ratio between hydrochloric acid and hydrogen?
2 to 1.
Okay, so for every 2 moles of HCl, we get 1 mole of H2. And then what unit do we have to convert back to? Back to grams. Here's the nice part. On this final step, you will always end with the same product. So if we already found the molar mass on like the first calculation, can we just copy it down here? Yeah. So then I know it's just 2.02 grams. What are we getting for this one?
0.1662.
Okay, so like 0.1662. Okay, so now we have to look at both of those answers. Okay. And how do you know which one is the correct one?
Smallest.
Okay, always the smallest. So which one's the smallest?
0.166.
Okay, so this one. And then this is where you can round it to sig figs. So you really get 0.166 grams of hydrogen. All right, the last thing we're going to talk about is something called percent yield. So the only thing you need on this equation is just this formula. Okay. So finally, when we're done with the reaction, we want to know how much product did we make compared to how much we should have made. Okay. So we call that the percent yield. So you just need to write down the equation. So the percent yield is just your actual yield divided by your theoretical yield times 100. So the actual yield is what you measure when you're doing the experiment. Okay, so like when I see you on Monday, we'll do a lab. I think you're making more copper. Okay, so it's like how much copper you actually measured, how much you made. When you're doing like a word problem, the actual yield is given to you. And then the theoretical yield, this is how much you should make in theory. Like if you were to have a 100% perfect reaction, this is how much product you should get. The theoretical yield, we always calculate using stoichiometry. Okay, so no matter what, you calculate the theoretical yield. And then the actual yield you either measure or it's given to you in the word problem. All right, so when we calculate percent yield, what percent do you think is like a good target? Like what number are you shooting for? What percent are you like trying to get when you do a percent? Okay, you ideally want 100%, right? Like you want to make as much product as you like possibly could. What are the odds of ever getting a 100% yield? Okay, slim to none. So let's talk about like why do we hardly not ever get a 100% yield? So some reasons, maybe your reaction just doesn't completely react. Was it last week when we mixed iron with like, was it copper sulfate? Okay. How many of you still had like the like silver iron like flecks at the top of your, okay, that just didn't clearly react. Okay, so when we say they don't fully react, things like that, where some of you still had iron just kind of floating at the top that never reacted. Sometimes it's due to impure reactants, especially like in our room, if people put like a contaminated utensil in the container, are you now contaminating your reactants? Okay, so then like you're thinking you have like just pure iron that's going to react, but if it's contaminated, then it's not fully going to react. And then finally, lost product. So if you have to transfer your material from like one beaker to the next, do you always lose some? A little bit. I always like to think of like baking. Like let's say if you're baking muffins, right? You got to like scoop your muffin batter out and into your muffin tray. Do you always have like leftover batter in the bowl? Yeah, so every time you like transfer your container, you lose some product that way as well. Okay, so we're going to do one practice problem where we just calculate the percent yield. Okay. So here we have this reaction where calcium carbonate breaks down into calcium oxide and carbon dioxide. So we want to know the percent yield if 24.8 grams of calcium carbonate is heated and it gives 13.1 grams of calcium oxide. So the first thing we have to do is just kind of make some sense of those numbers. So first, how much calcium carbonate are we starting with?
24.
Okay, so I'm just going to label the 24.8 grams. Okay, and then if you actually do this experiment, you heat it up, how much calcium oxide do you get? Okay, you get this 13.1 grams. This is the actual yield. We're going to come back to that number in a little bit. Okay, so we're going to ignore 13.1 for now. We're going to calculate the theoretical yield. And so since they measured out calcium oxide, that's what we have to do up here. Okay, so we want to know theoretically how much calcium oxide should we make if we have 24.8 grams. Okay. So you with me? We're going to use this number first. We're ignoring this number for now. Okay. You with me? Okay. So to figure out that theoretical yield, we have to do stoichiometry. We're going to start with the 24.8 grams of calcium carbonate. So we're starting here. We have to get to calcium oxide. Can you just go from grams to grams? Okay. What unit do you have to convert to? Okay, we got to get to moles. So what do you need to find to get from grams to moles of calcium carbonate? Okay, molar mass. So we all calculate the molar mass of CaCO3. All right, what's the molar mass of CaCO3? What do you, 100.9? Do y'all agree? Okay, so 100.09 grams. Okay, and then what's the ratio of calcium carbonate to calcium oxide? Does it look like 1 to 1? Okay. All right, and then finally we have to get it back to grams. So what's the molar mass of calcium oxide? Like, do you have 56.08? Are you getting 56.08? Okay, then go ahead and calculate this one just like you normally would. Okay, what are we getting? Okay, 13.89. I'm just going to round that to 13.9. Okay, so the number you calculate, this is that theoretical yield. Okay, so then the last step is to calculate the percent yield. It's just your actual over your theoretical. I'm just going to abbreviate that. Times 100. So do we know what the actual and theoretical yields are? Okay, so for the actual yield, that's the one given to you in the problem. So it's the 13.1. And then our theoretical, that's the one that you always calculate, which is 13.9. And then go ahead and divide those and then multiply by 100. Then multiply. So just divide first. So do 13.1 divided by 13.9, hit equals. And then did you times by 100? What do you get? I think you should be getting like 94.
Yeah.
Are you getting like 94.24? So you should be getting like 94.2%. I'll come help you look at it.